요즘 핫한 기술이다 이렇게 얘기하는 것 중에 하나가 웨어러블 컴퓨터, 웨어러블 디바이스 뭐 이렇게 얘기를 하죠. 어제 사실 서울 디지털 포럼에도 이 부분이 잠시 소개가 됐습니다만은 이게 이제 지금 가장 핫한 기술이고, 그럼 그 다음 기술은 뭐겠냐 이런 고민을 하고서 생각을 해보니까 바로 인공지능 기술 아니겠느냐 이런 얘기가 나왔습니다. 사람처럼 생각하고 사람처럼 행동하는 그런, 더군다나 사람의 감정까지 이해하는 기술, 이게 가능할지에 대한 이제 고민이 시작이 되는 건데요. 뇌를 컴퓨터로 복사해서 인공지능을 현실화시키는 그런 과정을 지금 연구하고 계시는 분이 있습니다. 유럽연합이 진행하는 휴먼 브레인 프로젝트라는 게 있는데요. 이걸 주도하고 있는 헨리 마크램 교수를 이 자리에 모셔서 기조연설을 듣겠습니다. 박수로 환영해 주십시오. Welcome, Excellency. Thank you.
Good morning. So what you just saw was millions of pieces of information that have been gathered over the past 100, maybe even 200 years that are coming together to form an integrated, unified, and holistic understanding of the human brain. Did you know that the world spends about $7 billion every year digging into different parts of the brain? Did you know that we generate so much data as neuroscientists that we don't even know what we know about the brain? In fact, the one thing that is common between this presentation and the next one you're going to hear about Watson is that what we have realized is that human beings can no longer understand what they are generating. We need machines to help us digest the information and achieve an understanding that is beyond what we individually can do. So the European Commission has awarded it's a historic grant of €1 billion to about 100 scientists around Europe and around the world to be able to solve this problem. And what we're going to do is to bring all this information together to try to build a digital model of the human brain and simulate it on supercomputers. Now, the drumbeat there actually is because the clock is ticking, and we're going to deliver that by 2023. The story is not that simple. What we need to do to understand the brain is not just to build a telescope like the Hubble Space Telescope to look very far and very wide into the brain, or to build a microscope that can look very deep and very narrow into the brain. We actually need to build a multiscope. We need to be able to look down at the level of the genes and the proteins and the cells, and to look further up as how these build together to produce all the magic that we know the brain produces and that you saw in Sherlock. So the way we're going to do that is to build a kind of Microsoft for the brain, or Google for the brain, where we're going to bring all the information that we have ever accumulated on the brain and bring it, upload it into this environment, organize it, because in some cases it's very messy, and it's different scientists producing different data. We're going to organize it, and then we're going to develop algorithms that connect all of this data to help us specify with as much detail as possible the entire structure of the brain. So with this kind of technology, we believe that we're going to be able to begin to explore some of the magic of the brain. For example, all the neurons, the universe of neurons. You have about 100 billion neurons in your brain. And in fact, if you look at all these fibers, if you had to unwrap your brain, you would have about 1 million kilometers of fibers. Enough to go, you could lasso the moon and back twice. It runs on 20 watts. So it is an incredible machine, and we need an incredible machine to be able to look at it and to understand it. When they form connections, or synapses, we'll be able to look at the entire universe of synapses. Your brain has about 1,000 trillion synapses. And each of these individual synapses, they're about this smaller than a bacteria. They each contain tens of millions of proteins that are used to build these synapses. And they convert electricity into chemistry. And there are about billions of these processes happening every second in your brain. And if there's a mistake in the way that electricity is converted into chemistry, then things go wrong. And if they do it exactly right, that's when you can get, hypothetically, a Sherlock. So we'll be able to go further to be able to start to do this and simulate how this works. We actually have to build new kinds of supercomputers. They do not exist today. We do not have the kind of supercomputers that can simulate the human brain. We need supercomputers that would be able to calculate at a speed of about 1 billion calculations per second. They need to be able to hold more than 200 petabytes of data in their memory system. So we have been building or designing these supercomputers together with IBM and perhaps with others as well. And that is going to allow us to obtain some of the first glimpses into how the brain is actually functioning when all these neurons are talking to each other and the proteins are interacting. Inside, not only to be able to look at the cells, but actually go inside a cell. Inside one cell, you have about 1 billion proteins. So you have 100 billion neurons, and inside each one is about 1 billion proteins and tens of millions of interactions that are happening. So it is a vast universe, and it is not impossible to start bringing all of this together. We will begin with the mouse. We will practice with the mouse. And we will put the brain, this digital brain, onto a virtual mouse. And right now, the mouse does not do anything really interesting. But the first thing it did is to start to dance. This is a virtual mouse, and it's going to behave in a virtual environment. And gradually, it will learn all the things that mice know how to do. So we'll be able to start exploring and get inside the brain. You see, today, I cannot get inside your brain to see how it works. I can measure it from the outside, but I can't get inside and look at what you see. But with this, you'll be able to step inside a brain and look at how it builds a world. And we believe that this is going to begin to help us understand how we create perceptions. How do we create the world that we live in? We do not see with our eyes or hear with our ears. We see with our brain. You are not seeing me. You're imagining me, actually, standing up here. Your brain is an imaginarium, and it is building this perception. And this way, we'll be able to begin to understand it. Now, this multi-scope will not only allow us to understand how the brain works from the molecular level, the microscopic level, all the way up to the macroscopic level, but we'll be able to start simulating brain diseases. But to do that, we need to know how to configure a brain disease. What changes do you make at the genetic level, at the molecular level, at the cellular level? What changes must you introduce? To do that, what we're also doing in this project is to begin exploring and actually gathering data from as many hospitals as possible, from millions of patients, and to obtain this data and to cluster it. What we want to do is to get a complete map of brain diseases. We think there are about 600 different brain diseases. And with this map, we will have specific signatures, genetic, molecular, cellular system signatures that we can use to configure these brain models and simulate that particular disease. This technology will not only allow us to understand the brain and to understand the brain diseases, but also to build the new kinds of computers of the future. Computers of the future are reaching an end because of the complexity of the requirement to program them. The brain does not need to be programmed. The brain learns. The brain is highly robust. You could lose half your brain before somebody notices it. So what we will do is develop the technology where virtual agents, virtual robots can learn the kind of tasks we would want them to learn, and then to take these circuit designs and to begin implementing them onto neuromorphic chips. And I think that the presentation is stuck. We'll begin integrating them onto neuromorphic processors. We're building two kinds of processors. One of them is based on the ARM processor, which is the same that is in your cell phone, and that runs at real time, and it can be attached to robots. So you'd have cognitive chips running that can run on these chips attached to robots, and the other one runs at 10,000 times faster than real time. And that will allow us to learn a whole array of different cognitive capabilities. So the other thing that we realized in this project, and that's what I mentioned at the very beginning, is that we realized that there is no individual scientist. There's no Einstein for the brain. It's not going to be one person who understands the brain. It's going to be not just one person, not just one country. It's going to be the whole world. And so what we're doing is we're building this technology to invite scientists, hundreds, if not thousands of scientists around the world to participate and to build software, to bring their data, to bring their expertise, to bring their medical knowledge, their engineering knowledge, and to collaboratively, collectively probe and understand the brain. We're also developing the technology to help train the future doctor and engineer and scientist in the future, because a doctor in the future is going to need to use machines and informatics and supercomputers and these kinds of simulations to help them make their decisions about the disease and to personalize the treatment that they provide, as an example. And lastly, we think it's very important to involve you, the whole public. And we're establishing a network of science museums around the world where the information about understanding the brain, or the future of understanding the brain, the future of medicine, and the future of computers would be available to anybody at any place in the world. And we're going to develop technology that will allow you to actually participate in the building of the brain, in the analysis of the data, in finding the data. So there will be a citizen participation component of this, which I think goes in line with the theme of the SDF conference this year. And we also think it's very important that we demystify brain diseases. You know, we have to realize that we all have problems. And actually, we need compassion and not judgment. And these things would help us to be able to make a lot more progress in terms of helping people with brain diseases, which today we believe is affecting about a third of the planet, costing probably 10% of worldwide GDP. You're looking at a $2 trillion per year problem. And we think that, that society itself can play an important role in it. And of course, lastly, to inspire the youth to participate and venture on this journey with us. So with that, I'd just like to thank you very much for your attention.